Now we will be studying about states of the program. When I talk about states of the program, what do I mean? I mean different paths or different times will or different steps will have different values of the variables. If you see this program, y is equals to 1, z is equals to 0, while z equals to x should not be true, then z is equals to z plus 1 and y is equals to y into z. Now, if this program is considered, first of all, what we do is we will write the variables that are given to us. So, if we see the variables, there are three variables in the program: y, z, and x. Y has the value 1, z has the value 0, x we don't know what the value is. This should be user assumed. Okay, so user has to put some value in x to make this program run. Now when we assume, let's say we assume 4 as an input. Now at the first command, which is y is equals to 1, here what we see is y is equals to 4, x is equals to 4, y is equals to 1, and right now we don't know what z is. Then when we come to z is equals to 0, x is equals to 4, y is equals to 1. Now we know the value of z is equals to 0. On the loop, where the loop is written, on the step where the loop is written, we know that x is equals to 4, y is equals to 1 and z is equals to 0. In the first iteration, we will then again use these values. In the first iteration, the first command or the loop body holds z is equals to z plus 1. X is equals to 4, y is equals to 1, but z will become 1, not 2, but 1. So we will correct this. This is not 2, but this will be 1. Z will be 1. Now, when we put in the value of z and y, because y is 1 right now, z is also 1 right now, it will be 1 and not 2. So this has to be corrected. Second iteration. In the second iteration, now the value of x is 4 and z is equals to 1, which is not equal. That is, we will go into the second iteration. Second iteration, we will have x because x is user assumed and will help us go through the iterations. The number of times the iterations will happen will be dependent on x and z. X is equals to 4, y is equals to 1 and z is equals to 2 in this case. When this is the situation, what we will have is y is in the next command, z into y, which is equals to 2, and z is equals to 2 only. Then we come on to the third iteration. X is equals to 4 and y is equals to 2 and z is equals to 2 again. So we go on. Here z is 2 and x is 4. So loop can go on. We will have iteration number 4 where x is equals to 4, y is equals to 2 and z is equals to 3. So in the next loop body, next command of the loop body, x is equals to 4, y is equals to 6 and z is equals to 3. Then we have another loop body here. What is the value of z? 3. Still not 4. If it's still not 4, we will go to the another iteration. X is equals to 4, y is equals to 6, z equals to 4. Then z equals to 4, x is equals to 4, y is equals to 24 and z is equals to 4. Now z value is 4 and the loop will become, if we see here, if we check the loop, now it will be 4 equals to 4 and it should not be equal. That is why we will have false. This is true and this is false. Once this becomes false, this is true and this is false. False will be the answer, and once we have false, we will not go into the loop. This is how we calculate or how our states changes. Now when we say We have variable x, y and z. What is this? This is the state. This complete thing is a state. So state is a set of all the variables and its values in a particular step of a program. So x is equals to 4, y is equals to 1, z is equals to, let's say, 0 in this case. And this keeps on changing throughout the program. If you would have seen, one or the other value is changing throughout the program. And to represent that, we use states. Why do we need states? Because when we are giving some input, we are getting some output. And when we are giving that input, we are assuming something and we are expecting something. From that input, we need to get to that output. And when we are getting at that output, what we are trying to do is we are trying to find how many states it changes and how it reaches the output. Is this a valid method to do it? Or is it possible to go through all these states and reach the output or not? This is something states help us recognize. So if somebody asks you what is states, the states of a computation is a snapshot. It is a snapshot which captures all values at a given step. At a given step, what you do is you capture all the values. If the program is in its initial state, then you call all the variables that hold value as initial values. Okay? And what does state do? State will always map the old state to the new state. So if you see here, when we were in iteration 1, iteration 1 was used. This is the old state and this is the new state. You can map the old state to the new state. Now state, then vector of length n and number of program variables. So what I did say before was that state is a vector of length n. This is the vector of length n. And what are these? What is this n? N is number of program variables. In this case, we have program variables as y, z and x. Okay. That is why we have vector of length n. So we have 3 values in one state. Now, after understanding this, we also need to understand why are we talking about triples. So programs will make some assumptions on their input parameters and formalize in phi. So I've already told that for input parameters, you have to make some assumption to get to the expected outcome. And whatever assumption you make, you represent that by phi. And whatever expected result you want to get, you represent it by psi. In between comes the program. So you give your assumptions to the program. The program results in psi. Psi is the output, the expected output. And when these 3 things are combined, it becomes a triple. If you say, I don't want the precondition, that is, we are not assuming anything, then what will happen? You will get unnecessary values out. If you say, I want the assumption from input, but I'm not considered about output, then your ultimate goal of meeting the expectation through the program will not get fulfilled. That is why we need all these 3 values, which are together called as Hoare triple. So, as I said, if you say, if there's phi, if phi does not hold true, then you will get any value, not specifically the one that you're expecting, but any value. Okay. Now we go on to another part where we say garbage in, garbage out. It is very important. So if you give an input that does not match the output, you will get output which is not expected. And not every state is admissible. That is, not every state is acceptable. So if you say, I have made a program for positive and negatives, 0 you're not considering in the program, then 0 is not an acceptable value. This state where the variables read 0 will not be admissible. Right? This is important to understand because it's not like that we are assuming the input and we are getting a specific output. But we need to understand that there are some reachable states that we can reach in order to fulfill the program's requirement. Okay. Now, if x is greater than equal to 0, y, this is an example, x is greater than equal to 0, y is equals to 1, z is equals to 0. This part, if you see, is the program. This is the program for factorial. Either you could have written it like this. If you didn't want to write like this and give a name to the program, you could have written like this also. Right? So the program could not work the same way with the negative numbers. That is, you're assuming that x has to be positive. If you see here, it says x has to be positive or a 0. It cannot work when the value of x is negative. If the program has no assumption on the input parameters, the precondition contains no program variables. It is just a constant true. Okay. One thing to analyze is, either you talk about phi or you talk about psi. What are they made up of? If you even see in this program, there's x greater than equal to 0, y is equals to x factorial. What are they made up of? They are made up of variable values. They are made up of variables. So the formulas that we construct are from the variables always. So if you talk about a precondition or a postcondition, or even when you talk about a program, the variables are the one playing the roles, and which is very important. Suppose you are not considering anything in the precondition, your precondition will be true. True means you are accepting all and any values. There is no restriction on the values. You are considering all the values that could come in and can affect the program. Right? Okay. So the goal we had was the correctness of Hoare triples. We wanted to check if the program is correct. The first thing that we wanted to check was that the program is correct. Now we will be going in depth and understanding what does this correctness means and how do Hoare triples help us in proving or in knowing if the program is correct. When in a Hoare triple, you have this as a triple, you already know by now. Okay, so when is a Hoare triple satisfied or correct? Okay, and when correctness is concerned, you're also talking about safety, liveliness, functional verification, etc. So if P runs in a state where phi holds, psi holds at the end. If your program fulfills the criteria of precondition, you say that psi, which is the postcondition, will also hold in the end. We will see some examples, actually a lot of examples to understand this. But what does it say? If a program, let's say there is a program and I take an assumption of phi, if this phi will hold in the program, if I am taking the right assumption, I will eventually lead to psi. See, if you remember implication that we were discussed in the last lecture, where we were talking about this sign called implication, what we were doing was phi, here is only one condition when it becomes false. If phi is true and the program is false, then the answer to these will be false. And we only don't want this to happen. So it can be anything but not false. Program cannot be false because if we are assuming right precondition, we will have a true values to the program, and if this is true, this should be true. It can also be false, but with right precondition, it cannot be false. Okay, so this is important to understand. Then, how do we check if we have entered or we have guessed the right invariant? Suppose we use assertion, and a lot of times we'll be discussing this when we'll be going to CBMC. Okay, now this is the important definition, can be asked. This is a definition. A Hoare triple phi p psi is satisfied under partial correctness, which is, see, you're saying satisfied. Again, in the first lecture, we had this symbol called satisfaction relation. This is satisfied under partial correctness if all states that satisfy the precondition phi. The state resulting from P satisfies the postcondition psi, provided that P terminates eventually. But this is not a necessary condition. P can terminate or P may not terminate. And now you will ask how. There are loops. If you remember when we were talking why we need deductive verification, here in the starting, you said this, that it can deal with infinite state space. There can be unbounded loops as well. And for those unbounded loops, sometimes the program will not terminate. But what we say, we are assuming that our program will eventually terminate in the partial correctness. Here what we are targeting is that the program should give the correct result and not if it is terminating or not. But when we move to total correctness, termination becomes really important. So a Hoare triple phi p psi is satisfied under total correctness. This is the symbol of total correctness. Then phi p psi if p terminates and the triple is satisfied under partial correctness. So partial correctness, so what is this? This is partial correctness. So you will prove by partial correctness or you will show that it is partially correct plus the termination. So the termination condition was not a part of partial correctness but is a part of total correctness. So you need partial correctness plus the termination to fulfill that the program is totally correct. Now, partial correctness is only focused on the correctness, whereas total correctness runs the complete program and produces the correct result. So it's not only talking about the correctness but also is talking about the termination of the program, right? Now, what are the methods of doing deductive verification? Right now, what we've understood is that we will either prove it partially correct or total correct. Then, now we need to understand either if we are doing it with a satisfaction relation, what it says is if all states, what it says here, if all states that satisfies the precondition phi, the state resulting from P satisfies the postcondition psi, provided that P terminates. So there should be all states that are true for phi and then the result should be true for psi. So manual proof is tedious. You cannot do the manual proof because phi can have endless number of states that you can put in and check. You do not know where it will fail. So either you are doing a manual proof, which is very tedious. You cannot take all the possible inputs and produce the output and check if it is matching or not. This is a very complex and a time consuming path. Whereas we have another method which is called Hoare proof. With Hoare rules, the proof can be mechanized. Now you do not need to put in 1000 values and see if it is true or not. You just need to mechanize through some grammar, through some symbols in order to automate a little. Not complete automation, but automate a little. The third and the final one, which will be the part of our last lecture where we will be discussing predicate transformers. Predicate transformer basically is that maps one predicate to another. One predicate. Predicate is a statement with all the operators, expressions, operators, and it will map one predicate to another. So what it does is, it proves Hoare triple by logical formulas. You will have logical formulas there and you will use verification condition and weakest precondition to show, to highly automate the stuff and find if it is agreeable that the program is correct or not. Coming on to a very, very important concept which will be needed for you to understand how these programs are generating variables which are abstract. Okay. When we talk about program variables, these are the variables that are actually present in the code. So if you say y is equals to 1, this is actually present in the code. If you say suppose z is equals to 0, you are assigning this value. This is something that is involved, can be seen in the in the code. Whereas there are other type of variables as well, which are known as abstract values. These are used in reasoning about the program's correctness. So this is not present physically in the program, but they play a very important role. And let me tell you how. So again, we have this program y is equals to 1 while x is not equal to 0, y is equals to y into x is equals to x minus 1, and the loop closes. This is factorial destructive program, name of the program, and this is the precondition, this is the postcondition. Now, if you make the diagram or understand this program, what you will find is we have two variables. This is the iteration. We have y and we have x. Initial value of y is 1. Let us suppose x is 2. Okay. Now y is 1 and x is 2. Or maybe let's take a bigger value. Let's say 3 because we want to see some iterations. Now x is less than equal to 0. X is 3. Yes, true. Now in the first iteration, what we will see? Y is equals to y into x. Y into x is 3. X minus 1, so 2. Then again it goes and checks 2 is not equal to 0. True. If 2 is not equal to 0, then if you see here, it's a second iteration and y into x is 6 and x minus 1 is 1. Why x is not equal to 0? True, still true. There's another iteration that we will have, which is third iteration. Now 6 into 1 is 6 and this is 0. Now it is equals to 0. The loop stops here. If you see, the last value of x is 0. And what we say is that once the loop ends, we will only store the last value of the variable in order to know what is the exact value going on in the program right now, and which is x is equals to 0. Now, this becomes a problem. The value of x becomes 0. But what we were trying to do was, we were trying to find the factorial of 3 and not 0. Right? So, here we understand that this x keeps on changing in the loop body. This x is not the x that we are focusing on. This was the user given x, but what we have right now is x equals to 0. So we say that if we include logical variables, if we say the assumed value is stored in here, x naught, this is logical variable, this is abstract value, cannot be seen in the program, but you say this x is assigned to x naught and x is greater than equal to 0 is the precondition. After the program is run, what you will have is y is equals to x naught factorial and x naught is 3. So you will have 3 factorial which is equals to 6 and this satisfies the program. Right? So this is how logical variables help us. But when we talk about this second question, here it's a Gaussian sum. Program of the Gaussian sum. Again, if you check out the iterations, we have again two variables z and x. Z is equals to 0. Let's say x is equals to 2 this time. It's a first iteration. First iteration 2 is greater than 0. True. Z is equals to z plus x, which is z is equals to 2. X will be reduced to 1. Now 1 is greater than 0. True. Second. Now 2 plus 1 is 3 and this becomes 0. Here it stops. Again the value of x is 0. If you put 0 plus 1 by 2, it's 1 by 2, which is not correct. To make it a correct value, which is actually 2, you will have to put 2 plus 1 by 2 and the sum will be 3 because 1 plus 2 is 3. So this is where we will need the logical variables because the values of x keeps on changing when it goes inside the loop. Hence, we need this when we are doing the questions. That is why we have highlighted this for you. Now, once you've understood this is very important concept and can be used a lot of times in the problems where we want to solve this, right? Okay. rub this one. Okay. Now we move on to Hoare calculus. So the set of proof rules that is syntax directed. I told you that either we do it manually. Here we were discussing either we do it manually. So either we put in the values and prove the partial correctness and total correctness, or we use Hoare rules or proof rules to mechanize the proof, or we use predicate transformer. So we've already studied partial correctness and total correctness. Okay, and we will also understand how we do it with partial correctness, total correctness. Second, we have proof rules, and third, we have predicate transformer. So now we start with the second one first to understand if we are making any sense or not. Okay, so this is the second part, Hoare calculus, mechanized proof, and before that was partial correctness and total correctness, normal, putting the values and getting it out. I will also discuss that as a question. So set of proof rules that is syntax directed, that is go along command subgrammar. There is a syntax that we have to follow because this is mechanized. There is a template sort of pattern created so as it is easier for people to go through it, right? So there is one rule per command and we have one additional rule called implied, which is very important. And now when you say that this Hoare triple is correct, you use the simple this one. This symbol is proof system symbol. Okay, and it works specifically on a template of inference rules. Now, what does that mean? We will have set of phi's, that is, there can be a lot of premises satisfying the program. But the conclusion that we want is just one. That is, if it is positive, negative, then we want that in the end, the conclusion is either positive or negative. And here we can give a lot of values. We can give 1, we can give -1, we can give -10, 100, whatsoever. So premises can be many, but the conclusion is one. This is an important concept related to reference rules, inference rules. Inference rules means if all of these are true in the program, we will eventually reach psi. Or if the conclusion, we want to reach a conclusion, or we have a conclusion already, we can go back as well to the premises. What values can we add, right? So this is how we are inferring. If one is true, we infer the other one is true as well. Valid sequence. Valid sequence is important because we are saying, we are checking, is this program P correct or does this hold all the correctness properties? And in this case, what we are doing is we are dealing with the sequent. This sequent, we say valid and sequent, two things. What is a sequent? This is a sequent. When you are writing a Hoare triple, it is called a sequent. And it becomes valid only when you are able to prove it. And how are you able to prove it? You will be able to prove it when you know the grammar, when you know the rule per command, when you know where is implied used and how it is used. Okay. So if we are able to prove something, it becomes a valid sequence. And how does it look? We will have a lot of Hoare triples. So there are Hoare triples that we have, and the Hoare triples conclusion will be inferred, or from in our conclusion we will infer the number of Hoare triples that comes in between. Okay. Now let's start with the proof rules, which are very important, and it is important to remember them because without them we cannot move forward. Okay. We start with implied rule. This is the extra rule. What is this? This is the extra rule. Now, proving Hoare triple partially correct. This is partially correct. What is partially correct? Doesn't need to terminate, right? So, x is greater than equal to 1, see psi. First case is, let us suppose x is equals to 1. We are taking one Hoare triple, which is x is greater than equal to 0 and see psi. And case number 2, which is Hoare triple 2, x is greater than 1, see psi. Now, we've taken two conditions. Either x is greater than equal to 0. I will tell you why we have taken this. And x is greater than 1. Now what we want to do is, the final condition that we want to reach is what? X is greater than equal to 1. This is the truth. But we say we cannot guess it in first place. X is greater than equal to 1. This is something that we cannot guess in first place seeing the program or the commands. So what we say, we take a little deviation, which is x is greater than equal to 0. When x is greater than equal to 0, what happens? Here we are taking a weaker condition. Weaker means if you are able to prove this, also 0 can be a part of it. There's no problem, right? So this is weaker condition because it covers more states. Here 0 is also a part now with 1. 0 is also a part and beyond. Obviously, it can go beyond. Now when we talk about Hoare 222, here we are missing one state, right? Which state are we missing? 1. Because this is x greater than equal to and this is x greater than 1. Now this is the stronger, covers fewer cases. It's holding less cases because 1 is excluded. Okay. So what we do is, we say if we are able to find the stronger precondition, if we are able to prove this, we can also prove this, which is if this satisfies this, then this also is true. This is original precondition needs to be strengthened. So this is the original precondition. Whenever we reach a weaker precondition, we can easily go to the stronger precondition. Now what do I mean by this if it's getting really confusing? X is greater than equal to 1. If this is true, then and this is false, then the answer is false. Because the weaker precondition is not satisfying, the answer is false. But if you are able to prove this as true, this is automatically true because this is a weaker condition. It has just number of states are increasing, but it's a weaker precondition. And this is how we show. So arithmetically, this is a valid sequence where stronger precondition is considered phi c psi I by phi dash c psi. If you prove a stronger precondition, then it helps to prove the weaker one. This is something that, so whenever you are doing the program, you will have something stronger, okay, like this. And your weaker precondition would be this one, x is greater than equal to 0. So you can say if this is true, this is also true. So I imply that this is true, okay. This is how you will use it. Now let's talk about postcondition. Postcondition will also have two cases, same, x is greater than equal to 0 and x is greater than 1. Here this is the weaker condition and x is greater than equal to 1. Proving weaker precondition doesn't guarantee a stronger one. If you prove that this is a postcondition, first of all, if you are proving a postcondition and if you write x is greater than equal to 0, what are you saying? You are saying that x will have, this is weaker because it's missing the 1, right? Why? See, if you're talking about this is a postcondition, we have to be strict with it. We cannot take a weaker postcondition because it will introduce one more state and this is not strong enough to prove, right? So if one value extra comes in, we are just not able to satisfy the program. Hence, we are taking the stronger precondition, postcondition, which is stronger. So x is greater than equal to 1 is stronger. So if you have a stronger postcondition, you can definitely say we can have this one as well. This one can also be true. If you have a stronger postcondition, you can definitely have a weaker postcondition to be true. And this is how we generally have the rule for implied. So, stronger precondition if you have, you can go to the weaker precondition. But if you have a stronger postcondition already, right? If you have a stronger postcondition already, what you can do is you can go towards the weakest postcondition. Okay. Now, here this is the standardized rule. Implied is not used like this in the program, but it is just used for importing. So if you've done Python, you import Python libraries. Similarly, this is the symbol that is not imported, that is not explained or proved in detail, but is directly imported. So you can infer directly saying this is true, then this is also true, right? So it doesn't need a complete proof from you. Second rule is composition rule. Composition means two commands together join and make a composition rule. If you see the maths of this or the grammar of this, if you see, what is this? The precondition, first command, the post condition. This is the post condition, and both the post conditions are same. In the second C2, we have psi, and we write this is the conclusion that this is a composition. But how do we know this is a composition? Because of these two same precondition, post condition, or we also call it as a mid condition whatsoever. So let's suppose this is our question. Okay, so this is phi, this is C1, this is neta, this is neta, this is C2, this is psi. Now you'll say this and this is same. Yes, but you take it this way. So you will write a is greater than or equal to 0. Then you will write both the commands. Z is z plus a equals to a plus 1, and z is greater than or equal to a. Okay, this is the complete program how you will write. So this always in the composition, this remains the same until the end. Now we come on to substitution. When we talk about substitution, we have a formula, we have a term, and we have a variable. So what will you do? You will replace the occurrences of x in phi in the formula with t. Okay, how? Let's see. So this is psi, this is what? This is the post condition, and here we have a command and we do not know the precondition. Now to know the precondition, what you do is the substitution. What you will do? X, here all occurrences of x will be replaced by t. So t is this, x is equal to x plus 1. So x plus 1 equals to 2. Then similarly, if you have x plus 1, x is equals to y. This is x plus 1 equals to y, because in x, instead of x you are putting x plus 1. Then again x plus 5 equals to y, x equals to x plus 1, x plus 1 equals to 5 equals to y, x plus 6 equals to y. Okay, this becomes your first precondition. But what I'll tell you is a little shocking. We do not have preconditions here. Then comes similar way, what you do is substitution. If you are talking about assignment, you're also talking about substitution in a way. Okay, so this is the formula. Here we are replacing y by w. So you see, instead of y we have w. Here we are replacing w with v. So we have v. If here we are replacing y with, this is directly here, y plus 1. So you have done y plus 1. So this is substitution. And the proof rule looks like this. Psi e by x, x is equals to e psi. This is the correct proof rule. Here we do not have a precondition. Is a shocking thing to understand. When we do not have a precondition with us, that is we have no premise, it is this, such things are called axiom. Okay, so the assignment rule is an axiom, right? So if we talk about the rule, here what we say, this holds in the state after x is equals to e, by showing that psi e by x holds before the assignment, right? So this holds the assignment, and after the assignment you will reach this state, but the wrong proof will be opposite of this. So you have the state, then you do the assignment, and then you do the substitution. So if this is the example where x is equals to 6, which is psi, then this is assignment, x is equals to e. Okay, and here finally what we have is, we have the substitution. That is, you will have 5 is equals to 6. Is 5 equals to 6 ever true? No, it is not. That is why we move forward And now we are coming towards the end of the first lecture, which is condition. Now we will do two more rules and we're done. But these two more rules are very important. First is conditional statement. In the conditional statement, you are always finding the precondition in every rule. Here in the precondition, you say if B, so how is it? If this condition is true, then do x is equals to x plus 1. Else, if this condition some other condition is true, you do x is equals to x minus 1. Okay, these are the two cases, conditional statements. That is why if will have one command and else will have another command to execute. And this is the precondition, this is the postcondition. Now how to find the precondition? To find the precondition, we need to understand this whole program will have two cases, if and else case, right? Now, if we talk about this is the grammar of it. So what it says, the precondition and the guard. What is the guard? Guard is something that comes in between, which is true, which is x is equals to x minus 1. Okay, condition 1, psi. Psi is x is greater than equal to 0. This is the first condition. Then the second condition. Now, you do not know, you know the phi. Do you know the phi? No, you do not know the phi. But either case 1 will work or case 2 will work. If is true, this command will be executed. If else is true, then this command will be executed. That is why if the guard is true, C1 will be executed, there is no negation. But if the guard is not true, C2 will be executed, there is a negation. And this is the formula for phi. If B C1, else C2 psi. Okay. Here is the guard. If proof rules exist, then it is correct. If proof rule doesn't exist, then it is incorrect. Now we talk about the final and the most important one, which is called as while loops. So here is the precondition, while. In the loop, there is a command that has to be executed. This is the branch. We haven't put anything in the branch yet. And phi is the post condition. Now, depending on the number of iterations, what we do is, now here we do not know how many number of iterations we will have, right? The question is, we are ready to unfold this, but we need to know how many number of iterations will this loop go on with. And sometimes we don't know that. Then how do we find? Let's say we do not know the number of iterations. So we write it like this. Okay. Here the precondition is neta I. Okay. And we unroll the loop. How do we unroll the loop? The loop can be unrolled with the help of if and composition, both. Okay. So first of all, neta I, B, C, and this is composition, while B, C, psi. Okay. Then we go up, we make it if, we use if. Neta I, if B, C, neta 2. This is the whole if statement. And then we separate if and while. While will have its own, if will have its own. Because this is the if statement, what we'll do is neta not B, C, neta 2. And then here what we have is while neta 2, if B, C, neta 3. And neta 3 while B, C is neta is psi. This is psi. This is the post condition. So what you do is unroll composition if while separate. Again if while separate. Do you see what you see here? What is common? There's neta term common everywhere. So this is N1, N2, N3, N4 and so on until Ni. This is common. What is this called? This is common factor. Irrespective of how many times are we running the loop, this is the common factor. And this is called as inductive invariant. What is it called? Inductive invariant. Invariant is something that holds true before the loop, after the loop, before the iteration, after the iteration. And the most important point is, we need something that is common, because if something is not common, we will not be able to prove. How will we able to prove? So finding this commonality is important. Here we will use the grammar as psi and b, which is branch true. If this is true, then a command runs and we reach psi. And here we say we have psi while b, c, psi and not b. That is, the loop will only stop if you can come out of the loop by negating or making the branch false, right? So this is how we do it. Now let's do a question to understand if we have understood the concept or not. First of all, invariant is something that will come again and again in the program while the loop is considered, right? So it makes it very easy for us to find the invariant and very hard as well for some programs. Right now, the method that I am telling you is the easiest one. We will also look into the another method when we move forward. So first of all, we set the iteration equals to 0. And when the iteration is 0, z is equals to 0, a is equals to 1. And here we scan which other elements or which other variables do we have. There's another variable y. Y is something that is, if it is not given in the program, you assume it because this is user provided. Let's say it was 3. Okay. Now, you go on to the first iteration. The first iteration says 1 is not equal to 3 plus 1, which is 1 is not equal to 4, which is correct. Okay. If it is true, the condition is true, you get into it. And z equals to z plus a. Z plus a is 1. A is equals to a plus 1, which is 2. And this remains 3. Correct? Now, because this is user assume. Now, second time 2 equals to 2 plus 1. 2 plus 1, 3. This is 3. Okay. And you can not equal. This is not equal and not as a factorial. So, do not confuse yourself here. 2 is not equal to 3 or 4. 4. This is 4 and not 3, right? Because this is fixed. 3 is fixed. Okay. Now you go inside and you say z plus a. What is z plus a? 3. And a plus 1. A equals to a plus 1. This is 3 again. And this is 3. Now we third equal 3 equals not equals to 4. And this is also true. So this loop will also go on 3. Here z is equals to z plus a 6. And a is equals to a plus 1 4. And here it is 3. Okay. Now very important. Very, very important. Now this loop will stop because now a becomes 4. And when it checks this, here a will check 4 not equal to 3 plus 1. Sorry. 3 because y is 3. 3 plus 1, which is 4 not equal to 4 is false. The loop stops and will not move forward. Right? This is what we have done to understand how the program will work in this case. Now we need to find an invariant. What do we need to find? We need to find an invariant. And to find that invariant, what we do is we see the definition of the invariant. The formula that holds true before the loop, after the loop, before the iteration, after the iteration. So before the loop, let's analyze this. First of all, what we want is always the invariant will be made with the help of the variables that are inside. Okay. These are the variables that are inside. Now, invariant will be made from z, a and y. These are the three options that we have. Okay. Now, what we are seeing is there's an output of z that is coming. How we will link it to this? We will do hit and trial. We will guess because invariants are to be guessed. We see 3 plus 1. Is it equals to 4? No. So this is plus addition can not happen. Minus 3 minus 1, 0. No. Minus cannot happen. Multiplication? No. That is also not true. How will we find then? So we will do hit and trial and understand the relationship between these numbers. These numbers will help us understand the relationship between each other. So what we do is, whatever is a minus 1 by 2. Let's suppose this is the invariant that we are taking in. Okay, this is the invariant that we are taking for the testing. So let us put the values. This should satisfy all of them. So 0, 0 minus 1 by 2. This is equals to minus 1 by 2. Is it holding? No, it is not holding. Okay. Now what we will do? Here we see that there is a problem. No invariant is holding. Now what we will do is, we will try something else. Now let us suppose we are checking z is equals to a plus y as the invariant. Z is equals to 0, 1 plus 3. Can it be true? No, this is also not the invariant. So this is how you keep guessing the invariant until you find one. Okay. No invariant is getting true. That means this needs another method. This needs another method to be found. I will not discuss that method again, but we will come back to this question once we reach that method. So this is one method of finding invariant, hit and trial, or you can use another method which we will be discussing further, and we'll come back to this question. Am I making sense? And with this, we have completed our first lecture on deductive